and what's called the eta squared, or 2 eta. You don't have to worry about why it's called that arrangement. And so what's happening is I started with a double bond, but now I'm going to form a single bond out of that carbon-carbon. But to do that, now I have to form 2 new bonds, and so they are formed to the metal surface. So each carbon still has 4 bonds: metal, carbon, hydrogen, hydrogen. And that's why they've switched back to that sp3 hybridization that they would have if they were in methane. Yeah?
Is there a catalyst that was supposed to bind like ammonia or red nitrogenous compounds?
Okay.
Would you also have to worry about it binding like free ammonia in the air, like from like an azide?
I mean, I don't know what you mean. It's going to bind ammonia from the air.
No, but also bind free nitrogen in the air.
Oh, you mean dinitrogen?
Yeah.
Yeah, dinitrogen can only fizzy-sorb to a surface without activating, without breaking the bond or having some lone pair, a pretty special metal, a pretty special surface that would actually form a chemical bond to dinitrogen.
Why would it form like an azide? Where the nitrogen binds into the nitrogen?
Well, I mean, you'd have to put something on the other end of that azide. Azides, the functional group for azide is not. An azide is. Does that make sense?
Yeah.
But nitrogen, you can attempt. I've just never seen it. I've tried to run it this way. To bind it like that, where you take a triple bond in the gas phase and you make a double bond and it forms 2 bonds to the metal surface. Every time I do it, though, it just goes up. It doesn't want to stick. So it'd have to be a very, very ignoble metal. So very far to the left side of the periodic table, something like, osmium might do it, something like rhenium might do it. But most metals most noble metals like platinum, nitrogen doesn't stick very strongly to the surface. All right, so those are some species that now we're talking about can chemisorb. The other things that can chemisorb are fragments of some of the other species. So, if I have methane, it fizzysorbs. But then if it reacts and I form CH3 plus a hydrogen, well, both of those species are chemisorbed, right? We didn't put them on our list because they're not stable molecules, so of course they chemisorb. They're radicals. They really want to bind to anything. So both a hydrogen atom and a methyl, this is also a chemisorbed bond. Let's see what Jason had in his notes that we might not have gotten to. Now, does the site matter? Does what I'm binding to matter in this case? Yeah, a great deal, right? For example, ammonia, it will bind to a metal, but it will also bind to what? Any guesses? What type of catalytically active site might ammonia bind to?
Enzyme.
An enzyme, certainly. What type of real catalyst? So what if I have an acid catalyst? So I'm going to call an acid catalyst here. I'm going to show the protons it's a Bronsted acid, and then I'm going to put B here just for base. So this is my acid, the whole thing, the proton plus the conjugate base. And why does ammonia stick to it? Why does ammonia interact so strongly with an acid? Because it's a base. Yeah?
But it doesn't bind to a hydrogen. You would have a double bond with hydrogen.
No, it does. No, that's a good point. So this is more of an interaction. This is more of a hydrogen bond. If it's a strong enough acid, though, it'll form this. And you'll still have a hydrogen bond to now the conjugate base. So it'll deprotonate the acid site. But no, I'm not saying that you're going to form 2 bonds, 2 formal bonds with a single hydrogen atom. That would be interesting chemistry.
Okay.
Technically, you can't do that, but not. Dative bonds don't require a participant. But
Is fizzy-sorption, was it when you just push it together and that's that?
yeah, fizzy-sorption is, right, it doesn't form a chemical bond. It's a physical interaction associated with these van der Waals-induced dipole-dipole moments. It's not forming a chemical bond.
Okay.
Whereas all these chemisorptions are. Yeah.
Does fizzy-sorption depend on the pressure a lot, or is fizzy-sorption might not?
They both depend on pressure. But it is true that the relationship between how much is absorbed and the gas phase pressure you could say they do have a different relationship when it's physisorption versus chemisorption. So you can get a monolayer of coverage at very low pressures from chemisorption. It's harder to do that from physisorption. You have to generally go to higher pressures or lower temperatures because it's so easy for the things to go back off into the gas phase. Okay, so this is site specific. And what do we think that the
What is site specific?
chemisorption? Just in the sense that you have to have a site that can form a covalent bond. For a lot of these, in some cases, you can form acid-base interactions as well. What do we think about the delta E of adsorption? Is it, compared to before, is it a stronger adsorption or a weaker adsorption? Stronger. So does that mean it's a larger number or a smaller number? More negative number. So less than negative, we'll put Jason's in, he had 50. I mean, I think that between 20 and 50, you're going to see both definitions. Physisorption and chemisorption can coexist in that region. It just depends on, you have to look at it. If you gave me a number, you said, I've got something binding at 30 kilojoules per mole. Is it chemical or physi? I didn't say, what is it? You know, I couldn't answer based alone on the binding energy. Okay, what about multiple monolayers? If I filled my surface with carbon monoxide, can I fit any more? No. Yes.
Is it possible to physisorb something?
Yes, I can physisorb a chemisorption active species. That is always possible. So that can be because the surface is inert, or what you're describing is because the surface is full. So the next carbon monoxide down can only physisorb, and it can still form a multilayer. Yeah.
Wouldn't carbon dioxide be better at physisorption than methane because it already has a dipole moment?
No, because it can form a chemical bond. It found something it likes to do even better than physisorb. Now, if you're talking about the multi-layers, I don't know. That's actually a good question. I haven't looked into it. Yeah.
Is it stronger for things like ammonia where you could still end up having hydrogen bonding with the physisorption? Would that be kind of chemisorption in the multi-layer sense?
If you have species that have an attractive self-interaction, then sure, but there's not a lot of species that do, which we would call gases at low temperatures. If they did, they wouldn't be gases at low temperatures, like water. You know, that's why water, is because of its ability to hydrogen bond with each other. But certainly it's easier to form multi-layers of water than it is to form multi-layers of methane. But that's partially just because it's easier to condense water in general. All right, one other thing that I'll point out real quick, because I just don't want it to become confusing.
Hey, Joe, do you want a multi-layer or no? Is there anything after the diffusion to the active site?
I'll say that you rarely run a catalytic reactor at conditions where you have to worry about multi-layers of adsorption for most things. You know, if I'm dealing with just normal molecules like the ones we put on the board, I don't have to worry about forming a multi-layer. You've got to be at really cold temperatures for that to be something that the molecule wants to do.
But it's not a desirable thing, right, for the rate of the reaction.
It only if you're right in that it prevented diffusion, then it would be an issue, but it wouldn't. So that's something we should talk about later. Technically, you can't be diffusion limited on a covered surface. Yeah.
This sort of is off the face or might not, but like, could you get a different product from the reaction from a physisorption and a multi-layer on top of something that's
I mean, again, you don't control whether you have that multi-layer or not. If you were to get a different product because you're at those conditions, it's because you're really cold, and so that's going to change your selectivity. But it's more about understanding how these molecules can interact with a surface that's important to be thinking about what's happening in a real system. But it's not something we can control. It's not like, oh, I can just make a multi-layer. It's physics. It does what it wants.
Is there math or just process?
We're going to have some math, yes.
All right.
You're not going to like the math, by the way. Okay, so if I start here at some 0 point and then I adsorb, so this is CO in the gas plus the metal, and then I have CO on the metal. again, a lot of times I'm going to use a star. Is the reaction energy for that process positive or negative? And so we're going to put delta E reaction is equal to delta E adsorption is less than 0. The reason why I want to point this out is there's another property, Q, that is defined as the negative of delta E adsorption. The other thing that I'll point out is that often you're going to see E and H used interchangeably when you're describing adsorption processes. Yes?
Is that because it's using the measured by calorimetry, which doesn't account for entropy?
It does account for entropy. All right, so there's two questions here. One, why is it enthalpy and not free energy? And that's the question about entropy. The second one is, why is it negative? It's negative because Q essentially means the heat released upon adsorption. So because that phrase is in there, heat released, it's the negative of the energy change within the system. So what I would calculate would be delta E, but if I were trying to explain this to an experimentalist, I might report it as an adsorption enthalpy of 120 kilojoules per mole. Even if it was, the value is negative 120, I'm just applying this Q is equal to negative delta H. The other question is more detailed than we need to get into, but you can measure either of those. If I'm going to measure the enthalpy of adsorption, though, the way that I generally would do that is calorimetry, and that is going to tell me the heat released. The other thing that you can do, though, is you can measure the delta G of adsorption, which is the free energy of adsorption at multiple temperatures. And if I get the free energy of adsorption at multiple temperatures, I know both the enthalpy and entropy component.
But isn't entropy also depends on temperature?
Yeah, but very weakly.
Yeah, isn't that the reason that I do things like you tend to do the calorimeters, like a basic calorimeter in your gen chem class is like the coffee cups or whatever, because it's a constant pressure, so it's not really that. It's like atmospheric pressure. Your dominant term is the change in temperature, which is enthalpy change.
I mean, you can do calorimetry at different pressures. The difficult thing with calorimetry is always measuring what is sure to be a very small amount of